Let's talk about transforming logarithmic functions from Lesson 5 of Algebra 2b Concepts. Our focus on this lesson is going to be, given a logarithmic expression, we'll describe how the graph differs from the parent function f of x equals log x. So remember, a parent function is the most basic of the function. It's the function that all other functions of that type are derived from. So when we dealt with linear functions, the parent function is f of x equals x. When we dealt with quadratics, x squared, cubics, square root, right? So it's the function at its most basic. So a logarithmic function at its most basic is just log of x. So we're going to compare expressions to this parent function and figure out how they've moved graphically. So this is our guide to what happens when you mess around with the parent function of logarithmic equations. So notice that if you have some expression f of x and you add to it, if you have some expression you add to it, the equation translates upward on the graph. If you subtract from it, the equation translates downward on the graph. Notice that this addition, this subtraction in this example is being applied to the function as a whole. Now if I were to isolate x, if I'm just subtracting some number from x or adding some number to x, this results in a horizontal movement, or moves left or right. If I subtract, I get movement to the right. If I add, I get movement to the left. If I multiply the entire function by some multiplier, it causes vertical stretch in the case of a whole number or vertical compression in the case of a fraction. Likewise with horizontal stretch and compression, if I, and notice this happens within x, it's attached to x, I horizontally stretch, notice it's the opposite, with a fraction, and I compress with a whole number. Reflection happens to the x-axis if I make the entire function negative, across y if I only make the x negative. So something I want you to take away from this, because you are welcome to use this, you can have this in front of you during exams. I don't expect you to memorize this sheet, but what I do want you to notice is that any time we do some operation to x and x alone, we end up with horizontal movement. Okay, so notice here I did something to x only. Here I did something to x only. Okay, and in both cases I had horizontal movement. Here I did something to f of x. Here I did something to f of x. And again, vertical, vertical. So this makes sense, right? Because f of x equals y. So anything we do to y, if f of x equals y, anything we do to y is going to be vertical, and anything we do to x is going to be horizontal. And this matches with the way we graph anyway, right? Our y-axis runs up and down, our x-axis runs left and right. Alright, so let's do a couple examples. So what do I mean by comparing to a parent function? What did I mean by all that? Well, let's say you're given g of x equals 5 times the log of x minus 2, and you're asked to identify how has the graph changed. Well, if my original expression is f of x equals log x, what have I done to change it? Well, one thing I've done is I've subtracted 2. And now I didn't do this to just x, I did it to the entire function. So what happens when you add or subtract something from the function? It results in a vertical translation, as you see here. So that means I've shifted the entire equation down by 2, or you could say a vertical translation of negative 2. But that's not all I've done. I've also multiplied by 5. I've multiplied the expression by 5. So what happens when I do that? Well, as you see here, if I multiply the equation by a whole number, that means a stretch, a vertical stretch. So I've vertically stretched by a factor of 5. So those are the two things I did to change this equation and make it different from my original parent function. Let's do another example. Alright, what have I done here? My original equation was f of x equals log of x. Well, it's pretty easy to see that one thing I've done is I've made x negative. Now notice this negative is attached to the x, it's not on the outside of the equation. It's x alone. It's x alone. So what does that mean? Well, when you have f of negative x, as I've done here, it means I've reflected across the y-axis. So one thing I've done is I've reflected across the y-axis. Okay, what else have I done? Well, you can see I've added 8. Notice that 8 is within the parentheses. So I'm not adding 8 to the entire equation, I'm adding 8 to this expression in the parentheses. So that means horizontal translation. I've added 8, and you can see when I add numbers, I go to the left. When I add numbers, I go to the left. So I am horizontally translating left 8 units. So those are the two things I've done that are different from this original parent function. Let's do another. Now I have negative log x plus 6. So again, comparing to that original, what have I done differently? Negative log x plus 6. Well, now this negative is being applied to my actual logarithm. Okay, so just as we have here negative log x, that means I am reflecting across x-axis. I've also added 6. Notice that this does not lie within the parentheses, it's happening to the whole equation, which means it's a vertical translation. So the second thing I am doing here is vertically translating upward 6 units. Okay? So I know that this f of x notation doesn't always make sense, but these examples are awesome that they give you. So notice that I'm able to kind of match up like, oh, this negative log of x, I see it matches what this one looks like. Use that to help you match up what's going on here, and then pay attention to how they explain what's happening to the examples. All right, let's do one more of that kind. So what if I have log of 1/3 x? How does that differ from just plain old log x? Well, pretty easy to see. I've multiplied the inside of this logarithm, the quantity of x, by 1/3. So take a look over here. I see the same thing, 1 over b. So what does it mean if I have 1 over 3? Well, that kind of looks like this one. So in this case, they said it's stretched by 5. So in my case, it must mean I stretch horizontally by 3. So I've done a horizontal stretch by a factor of 3. Okay? Now, notice that we've been given the equations and we've been telling them how it's changed. But what if we're told how it changed and we give the equations? That might be a little more complicated. So, we have this original parent function, f of x equals log x. Okay? And we're going to manipulate it based on the statement they've given us. So they say that we're going to shift 7 units left. Let's take care of that first. So going left and right means horizontal translation. And to shift left, we see that we must have an addition sign in there. So we're going to add 7 to x. Notice that it's within parentheses. Okay. So what about reflecting across the y-axis? Okay, well, I go to my reflection row. Reflection across y happens when I take f of negative x. Reflection across y happens when I take f of negative x. So that means I must have a negative sign in here. Okay? So log of negative x plus 7 would reflect a shift 7 units to the left and a reflection across the y-axis. Let's do another. So once again, I'm told to write the transformed function, and the best way to start is by writing the parent function. So f of x equals, and I just write log x, and I leave myself space to add in more information. So in this case, I shifted 7 units right, so let's take care of that first. Shifting right and left is a horizontal translation. So I see that to shift left means I'm adding, right? So in here, that subtraction led to shifting right. I want to shift left, So I'm going to subtract 7 and add parentheses. I also want to shift 4 units up, and it looks like vertical translation, going up and down, happens when I add something to the function. So I'm going to add 4 onto this. So I find that my function is equal to the log of the quantity x minus 7 plus 4. This means I've gone right 4 units right 7 units and up 4. Let's do another one. All right. So again, I'm going to start by just writing the parent function, f of x equals log of x. So what do I need to do to this? Well, I want to horizontally stretch by a factor of 2. Let's go to horizontal stretch. Stretch happens, a whole number stretch, so in this case stretch by 5 happened when I multiplied by 1 over 5. So if I want to stretch by 2, I'll multiply by 1 over 2. Okay. What if I want to reflect across the x-axis? Well, I go to reflection, I look at the one that says across x, and I see that they multiplied f of x by negative, so I'll just put a negative sign out here. So my parent function was f of x equals log x, but I've reflected it across the x-axis, and I've horizontally stretched it by a factor of 2. So that's f of x equals negative log of 1/2 x. Let's do one more, and we'll wrap up. So, write the transformed function for f of x equals log x is vertically stretched by a factor of 6. Okay, so once again, writing my parent function. So let's see, f of x equals log x. So now I'll add in what they've done to it, and all they've done is vertically stretched by a factor of 6. I go to the vertical stretch row. I see that when they multiplied by a whole number 6, it caused a stretch by a factor of 6. So if I want to vertically stretch by a factor of 6, I'll choose 6 as well. So f of x equals log of 6x means that I have taken the parent function and vertically stretched it by a factor of 6. So again, I recommend, you'll see this table as you click through the presentation in your course. Either copy it down in your notes, take a photo of it, print it out, do something, take a screenshot of it, keep it handy, because I doubt you'll memorize it and you're going to need it to answer all of the questions as you go through this lesson. See you next time, guys.